Hi everyone, I'm Shuichi Hirahara from National Institute of Informatics. Today I would like to explain how to view pseudorandom generator constructions from a meta-computational view. Let me start with explaining the title of this talk. Let's recall the notion of promise problems. A promise problem is a pair of yes instances and no instances. And we usually require that yes and no instances are disjoint. The idea of a promise problem is that we promised that the input comes from yes instances or no instances. So we say that an algorithm A solves the promise problem pi if every yes instances is accepted by the algorithm and every no instance is rejected by the algorithm. Pictorially, we can draw a picture like this. So the algorithm A separates yes instances from no instances. What we consider in this work is a non-disjoint promise problem. We say that a promise problem is non-disjoint with double quotation mark like this if it is believed that yes instances are no instances are intersecting. If you think about it, it's a quite weird notion and it doesn't make sense if there is an input x which is both yes and no instances, because in that case, we can't separate yes instances from no instances. So there is no algorithm A that can solve the promise problem. But surprisingly, what I'm going to try to do today is to convince you that there are a lot of interesting non-disjoint promise problems which are quite worth investigating. And I'm going to present a set of non-disjoint promise problems based on any pseudorandom generator constructions. What we consider in this work is what we call non-disjoint promise problems. We say that a promise problem is non-disjoint if it is believed that the set of yes instances and no instances are not disjoint. If you think about it a little bit, you can find that it is a quite weird notion in the sense that if there is an input x which is both yes and no instances, then we can't separate yes instances and no instances by any algorithm. So in that case, there is no algorithm A that can solve the promise problem. Nevertheless, what I'm going to do today is to try to convince you that there are a lot of interesting non-disjoint promise problems which are worth investigating. And in order to do that, I'm going to introduce a set of non-disjoint promise problems based on any pseudorandom generator constructions. Next, let me review the notion of pseudorandom generator constructions. The Hardness versus Randomness Framework was developed around 1980s. One of the landmark results of Hardness versus Randomness Framework was given by Impalgas and Peterson, which states that if we have an exponential size circuit lower bound for the class E, then we can solve BPP in deterministic polynomial time. What they actually showed is something stronger. They actually constructed a pseudorandom generator which is secure against linear size circuit and computable in polynomial time. Here, a pseudorandom generator is a notion which extends S-bit seed to M-bit pseudorandom sequence such that if you take any algorithm T in the class C, then the algorithm T can't distinguish the pseudorandom sequence from the uniformly at random strings. What actually they showed is actually much stronger than that. They actually constructed a generic pseudorandom generator construction which takes any head function f, which can't be computed by exponential size circuit, and convert it to a secure pseudorandom generator G superscript f, which extends its seed exponentially. So the point is that in the hardness versus randomness framework, we can take any hard function f and we can convert it to a secure pseudorandom generator, G superscript f. In this talk, I'm going to give a meta-computational view of pseudorandom generator constructions. Now let me explain the idea of meta-computational view. In the traditional hardness versus random framework, we usually think of a function f as a fixed hard function. And what the framework tells us is that if we can find a hard function, then we can build a secure pseudorandom generator based on the hard function. And the conclusion of the framework is that if we can have a circular overbound for an explicit function, we can get a secure pseudorandom generator. Actually, we can prove the converse direction as well, but it's only for a sufficiently large class C which can compute majority, because in order to prove the converse direction, we need to use worst case to average case reduction. What we do in this work is to view a pseudorandom generator construction from a meta-computational perspective. In particular, we don't fix a hard function. Instead, we are going to regard a function f as an input to some non-disjoint promise problem. Let me give one example, which we call the E versus exponential size circuit problem. Informally, this problem is defined as a following promise problem, whose yes instance consists of a function which can be computed by exponential time with linear size advice, and no instances consist of a function which cannot be computed by an exponential size circuit. And what I'm going to do is to regard a pseudorandom generator construction as a reduction that proves a security of some hitting set generator. And what we are going to prove is that by using that, we are able to prove the equivalence between the existence of a hitting set generator and a such lower bound for some non-disjoint promise problem. For example, we can prove that the E versus exponential circuit cannot be solved by linear size AC0 over XOR circuit if and only if there is a hitting set generator secure against AC0 XOR circuits. What's interesting about this is that in order to get a hitting set generator, we just need to prove a linear circuit size lower bound. In the rest of my talk, I will first introduce a set of problems which we call MCLPs, and then I will give a definition of the E versus exponential circuit problem. The hardness versus random framework tells us that if we can prove a sufficiently strong circuit lower bound, then we can get a secure pseudorandom generator. But the question is how we can get such a circuit lower bound. In fact, it is an open question to prove a superlinear lower bound for exponential time computable function. Now, I'd like to pose the following question. Why is it so difficult to prove a circuit lower bound for an explicit function, such as exponential time computable function? I'm not going to give an answer to this question, but instead, I would like to introduce a new framework to investigate this question. To do that, I'm going to propose a way to view this question from a meta-computational perspective. Specifically, I would like to introduce a family of promise problems which we call Meta-Computational Circuit Lower Bound problem, which we call MCLP for short. In this problem, you are given the truth table of a Boolean function f, and the task is to distinguish whether f is an explicit function or a hard function in several senses. So the idea behind this definition is that the hardness of MCLPs should capture the difficulty of distinguishing hard function from explicit functions. And morally, this should be equivalent to saying that it is difficult to prove a searched robot for an explicit function. So by investigating the complexity of MCLPs, we should be able to answer the question whether proving a searched robot for an explicit function is difficult. Let me give one example. So one example is a E versus exponential size circuit problem. So as we said, informally this problem is defined as follows. As an explicit function, we take a function f which can be computed by exponential time with a linear size circuit, and as a Hirahara function, we take a function f which can't be computed by a polynomial by an exponential size circuit. As the name suggests, it is actually related to the open question of whether E can be simulated by exponential size circuit. Let me explain this in the next slide. We can observe that the E versus exponential size circuit problem is non-disjoint if and only if there is an exponential circuit lower bound for the class E. This is because of the following simple fact. If we have an exponential circuit size lower bound for E, then it is equivalent to saying that E with linear size advice can't be simulated in exponential size circuit, which is equivalent to saying that we can find a function f which is in S instance of the E versus exponential size circuit problem, and it is also hard in the sense that the function can't be computed in by an exponential size circuit. Let me explain the formal definition of the E versus exponential size circuit problem. First, I would like to clarify the meaning of size of S of n. That can mean several classes. One potential class is that for a function S, usually size of S of n denotes the class of functions f, which is defined on all the inputs, and for all large n, the such complexity of the function f is bounded by S of n. But this is not the definition I'm going to use. I'm using here. The definition I'm using here is that for integers s and n, we define size of S of n as the class of functions f, which takes n bit input, and it is a Boolean function, and the such complexity of f is at most s. This is the definition of size. So we can rewrite the no instance of the problem as the set of function f which takes n bit input, and the such complexity of f is at least 2 to the little order of n. Next, I'm going to clarify the yes instances. Usually, E/order n usually means the complexity class which can be solved in time 2 to the order n with linear size advice. And in that case, we usually consider a function f which is defined on all the inputs, not just a n-bit function. Instead, I would like to interpret the complexity class as a subset of a function f which takes just n-bit function. And in order to do that, I'm going to use Levin's resource-bounded Kolmogorov complexity. Let's recall the notion of Levin's resource-bounded Kolmogorov complexity, which is usually denoted by capital K, small t. So, informally speaking, Levin's KT complexity over a finite string X is defined as the minimum of the length of program M plus log of the time bound T, where we take a minimum over all program M and the time bound T such that the program prints X in time T. In order to make it formal, we fix an efficient universal Turing machine U, and KT of X is defined as the minimum of the length of T plus log of t, such that the universal Turing machine outputs x in time t. Now, in order to define E/order n as a subset of a Boolean function that takes n-bit function, we use the following fact. For any function f, it is equivalent to saying that f can be solved in exponential time with linear size algebras if and only if the kt complexity of the function f sub n, where f sub n is a restriction of f to n-bit inputs, the kt complexity of f sub n is at most order of n for all large n. So by using this fact, we can regard E/linear size algebras as the class of an n-bit function whose kt complexity of f is at most order n. So the key idea behind this fact is that the length of an algebra string can be regarded as a program size in terms of Kolmogorov complexity. Using the notion of kt complexity, we can define the set of yes instances of the E versus exponential problem as a class of n-bit functions such that the kt complexity of f is at most order n. What remains is to deal with the asymptotic notations such as order of n and 2-digit order n. This is problematic because we are fixing n, so we can't use asymptotic notations. In order to avoid that, we regard the E versus exponential size problem as a family of promise problems, where we parameterize promise problems by using a constant c and alpha. And I'm going to replace order notation here with a constant c, and we define yes instances as a set of function f whose kt complexity is at most c times n. Similarly, I'm replacing little order notation with alpha. And we say that a family of promise problem is solved by a class C if for any promise problem in the family, if there is an algorithm that can solve the promise problem. Now I can give the formal definition of the E versus exponential size circuit problem. So the problem is defined as a family of promise problems where the promise problems are parameterized by C and alpha. And the set of yes instances consists of a function f which takes n-bit function, and the kt complexity of f is at most c times n. And the no instance of the promise problem consists of n-bit function whose circuit complexity is at least 2 to the alpha times n. This is a rather technical definition, but what you should keep in your mind is that these yes instances and no instances capture the complexity classes E/order n and the complement of the exponential circuit classes, respectively. Now let me state our result. Our result shows that if we can prove a lower bound for MCLPs, then we can construct a heating set generator. Moreover, in most cases, we can prove the converse direction as well. So we actually get an equivalence between a circuit lower bound for Meta-Computational circuit lower bound problem and the existence of a heating set generator. So here is one of our main results. We can prove the following equivalent. The first condition states that there is an explicit heating set generator secure against linear size AC0 XOR circuits. We can prove that this is equivalent to a circuit lower bound for the Meta-Computational problem. Namely, the second condition states that the E versus exponential size problem can't be solved by AC0 XOR circuit of nearly linear size, where capital N denotes the length of the input. If you don't like our notion of non-disjoint promise problem, we can actually state our result without using the notion of non-disjoint promise problem. MKTP is a standard promise problem which asks whether a given string X has KT complexity at most order log n or at least n to this little order of 1. We can show that the existence of a heating set generator secure against AC0 XOR circuit are equivalent to proving a lower bound of MKTP against AC0 of XOR circuit of nearly linear size circuit or fixed polynomial size circuit. One thing we should not emphasize is that these statements are much stronger than proving NC1 lower bound for EXP, so these are open questions. So what our result suggests is that in order to resolve these questions, we can just prove a superlinear circuit lower bound for these problems. Now let me compare our result with the hardness versus randomness framework. In the hardness versus randomness framework, we need to find an explicit Hall function. And once we construct an explicit Hall function, we can construct a pseudorandom generator. Let's take a look at this from a meta-computation perspective. Namely, we would like to consider the E versus exponential circuit problem. Now, if we can find an explicit Hall function, this means that we are trying to find a function f, which is both yes and no instances of the E versus exponential size circuit problem. And this is equivalent to proving a very strong lower bound for the E versus exponential size circuit problem. Because if we can find an intersecting point of yes and no instances, it means that there is no circuit that can solve the problem. So in other words, this is equivalent to proving an infinity size circuit lower bound. What we showed in this work is that we don't have to prove such a very strong circuit lower bound. Instead, we just need to prove a nearly linear size AC0 XOR circuit lower bound in order to construct a heating set generator. A natural question is whether it is feasible to prove a circuit lower bound for the meta-computational circuit lower bound problems. We can actually prove that if there is no bottom XOR layer, we can prove a circuit lower bound. Namely, by using a pseudorandom restriction method, we can prove that the E versus exponential size circuit problem can't be solved by AC0 circuit of size n to 100, for example, or any constant. Now, if we can extend this AC0 lower bound to AC0 over XOR circuit, then we can get a breakthrough result which separates EXP from NC1. Let me try to convince you that we are making a progress towards constructing a heating set generator unconditionally. In order to explain that, I'm going to use a case analysis. So let's consider the following two cases. Either it is easy to prove a circuit lower bound for an explicit function, or it is difficult to prove a circuit lower bound. Of course, we believe that it is difficult, but there are at most two cases. In the first case, namely, if it is easy to prove a circuit lower bound, then someone should have already been able to prove a circuit lower bound. In that case, by using the standard hardness versus randomness framework, we can get a pseudorandom generator. So that's fine in this case. Now, in the second case, namely, let's say it is difficult to prove a sagital one for an explicit function. In that case, we should be able to prove a very mild sagital one for MCLPs, because MCLPs in some sense capture the difficulty of distinguishing explicit functions from hard functions. So when it is difficult to prove a sagital one, we should be able to prove that it is difficult to distinguish explicit functions from hard functions. Now, if we can make this intuition formal, by using our result, we can get a construction of a hitting set generator. So the point is that in both cases, we can get a hitting set generator construction. Of course, the main difficulty is that there are a large gap between the first case and the second case. But by trying to make this argument formal, probably in the future we can get a new construction of a hitting set generator. Our result can be applied to other derandomization questions. One of the central questions in the theory of derandomization is whether randomized log space can be derandomized, namely whether RL is equal to L. By applying our meta-computational view, we can prove the following theorem, which states that if we can prove a read-once non-deterministic branching program of nearly linear size can't compute the linear space versus approximately exponential circuit problem, then we can prove that RS is equal to L. This can be seen as a generalization of the Hardness versus Randomness Framework result, which was given by Krivans and van Merkbeek. Our result can be also applied to the case of uniform algorithms. By applying meta-computational view, we can prove that a uniform lower bound for MKTP is equivalent to proving the existence of a derandomization algorithm for uniform algorithms. Let me briefly explain our proof techniques. What we show is the following general principle, which takes any pseudorandom generator construction and regard it as a security proof of a hitting set generator. To be more specifically, let's take a pseudorandom generator construction G superscript F, and let's say it is based on a hard function, F is not in R. Then we can regard the pseudorandom generator construction as a security reduction of some hitting set generator H, and the security of hitting set generator is based on the hardness of some non-disjoint promise problem, such as E versus R problem. As a choice of a hitting set generator, we take a time bandit of a universal Turing machine. In some sense, this is a universal choice of a hitting set generator. Now, in order to prove the security of the universal hitting set generator H, let's say we have an oracle D which violates the definition of the security of H. Now, in order to prove the security of H, I'm going to present a security reduction, which is quite simple reduction. So here is the randomizer algorithm that solves the E versus R problem given the oracle D. Given the input F, which is an n-bit function, we just pick a random seed S, and we just output the negation of D given the pseudorandom sequence as input. That's the security reduction, and we can prove that this gives a security reduction of the hitting set generator. By using our framework, we can define other non-disjoint promise problems. And in the paper, there are several other results, which is given by viewing other constructions of pseudorandom generator constructions. To conclude my talk, we have generalized the hardness versus randomness framework by using a meta-computational view of a pseudorandom generated construction. And in order to do that, we have introduced meta-computational such lower-bound problems, which are problems of distinguishing explicit functions from hard functions. And what's interesting is that if we can prove very weak lower bounds, then we can get a breakthrough result and we can get the construction of a heating set generated.